In this lecture, we are going to discuss some results on convergence of sequence in a metric space. In a metric space, every convergence sequence, is a Cauchy sequence. In the statement of the theorem, it was helps to show that every convergence sequence is a Cauchy sequence. Proof: let us consider action in X such that action converges to X in X. Okay? To show action is Cauchy sequence. So every convergence sequence is a Cauchy sequence. First, we have considered a sequence action in X such that action converges to X in X. We have to show action is a Cauchy sequence. Since action converges to X for epsilon greater than 0, there exists some and not belongs to L such that distance between x and comma x is less than epsilon for all n greater than n. This is from the definition of convergence of sequence. Therefore, for all m comma n greater than equal to n, we have distance between x and x is less than, take this epsilon by 2. Okay, this is epsilon by 2, and distance between x and comma x less than epsilon by 2. Since epsilon greater than 0 is a pre-assigned positive, a small positive quantity, we can take this epsilon by 2. Okay, so for all m greater than equal to n, we have d of x and x is less than epsilon by 2 by this definition, and dx and x is less than epsilon by 2 by this definition. Therefore, it is to therefore it is to x m x plus g of x m x is less than epsilon by 2 plus epsilon by 2. This is less than epsilon. Therefore, d of x m x plus, by using symmetry property of a matrix, since D is a matrix, I can write this instead of that. Instead of this, I can write this one. This is less than epsilon. Again, by using triangular inequality, instead of this, I can write this one. Okay, that means our given sequence is this is for all m and greater than equal to n. That means our given sequence is a Cauchy sequence. A Cauchy sequence. Cauchy sequence. However, the converse of this statement is not true. That is, every Cauchy sequence is not convergent. Consider right, before that you should write, however, the converse of the above consider the sequence 1 by n in the space 0, 1. Let we are going to show that this sequence is a Cauchy sequence. First, let us choose epsilon greater than 0. There exists positive integer, positive number n not greater than epsilon 2 by epsilon. Okay, no, 2 by epsilon. That is 1 by n naught is less than epsilon by 2. Therefore, for all m comma n greater than equal to n naught, 1 by m 1 by n less than equal to 1 by n naught. Okay. Therefore, take the distance between we are going to find out the distance between xm and xn terms. This is here our sequence is this one. So distance between m minus 1 by using the properties of modulus. This is equal to 1 by m plus 1 by, okay. This implies d of xm xm is less than equal to 1 by m is m and n are natural numbers. So this is 1 by m positive number. So modulus will give you positive. And this is less than 1 by n naught, and 1 by n naught is less than epsilon by 2. So this is less than epsilon by 2. This is less than epsilon by 2. By same argument. And this is equal to epsilon. So you should write for when m n when m n greater than equal to n. This implies d of xn less than epsilon for all m comma n greater than equal to. This implies 1 by n is the Cauchy sequence. This sequence is a Cauchy sequence. This sequence is a Cauchy sequence, but the point to which this sequence converges is not in this space. This sequence converges to 0, but 0 is not included in this space, so this sequence is not convergent. So right, but the point 0 to which one to which the sequence 1 by n converges is not in the space 0, 1. Therefore, 1 by n is not convergent. Is not convergent in 0. Hence, every Cauchy sequence is not convergent. Hence, here we have shown that 1 by n is Cauchy sequence. Here we have shown that this is not convergent. Hence, every Cauchy sequence is not convergent. With that, I would like to conclude. Remaining will be in the next